welcome to Module 23 on Feature Engineering Principles. So today we're going to talk about why features often matter as much, I should put quotes there, as model choice. We'll talk about common feature types and transformations, good feature engineering practices, how to avoid data leakage, common theme in the course, how to use pipelines to keep everything honest and reproducible, again a common theme. And we'll see some worked examples in Python, which we'll get to momentarily. By the end of this module, you should be able to explain what feature engineering is and why it might matter for generalization. You'll be able to classify features into numeric, categorical text, and so on, and choose suitable transformations. You'll be able to diagnose potential data leakage in a feature set or processing pipeline. You'll be able to implement simple scikit-learn pipelines that combine preprocessing and models safely. A bit of redundancy there, but it's slightly different also. And you'll be able to justify feature choices and transformations in terms of data generating assumptions and evaluation goals. So a feature, we're going to define it now. This is a measurable property or attribute that you feed into a model. This can be tabular, like age, income, number of logins per week. It can be an image, like pixel intensities, edges, CNN activations. It can be text, like word counts, TF-IDF statistics, embeddings, or graphs, like statistics on graphs, like degree, centrality, cliqueiness, graph-based statistics. I indicated CNN activations and embeddings with little pointy fingers, just to emphasize this one point. Historically, features, as we'll define it in a moment, have been sort of small little results of small little computations that we applied on the raw data. So we get some super raw data, maybe like an image or something like that, and we wanted to compute the overall edginess of the data, or something related to like statistics of intensities or edges, how many edges exist in this image, and then we pass like those statistics which we pre-computed to the model. So the model wouldn't necessarily see the pixels; it would just see a vector x of inputs, but those x would be the result of these small little computations, which we called features. However, as we moved to deep learning and modern neural networks, the inputs kind of regressed and became just the raw inputs themselves. So just the pixels, just the raw words, or even just parts of words, or the letters. And then we still wanted to do all the kinds of predictions we were doing, with the setup I mentioned a moment ago. And I'm not sure if, which direction, whether the chicken or the egg came first in this regard, but it turned out that we ended up calling features more intermediate representations of neural networks somewhere in the process. So whether it was like one big model that took raw pixels and then computed some information on those pixels, and then that information encoded something useful about the data, like it separated the data in some way, and then that was later used downstream in the same model for classification, for regression, whatever. Those little representations were called features. And there's pros and cons about this. The good thing is that it serves the same purpose. Like the model is transforming the data in some way. It's a measurable property or attribute that is going to be fed into a classification model. We should call it a feature. So it's consistent, all good. A bit of a challenge is this. I'm probably getting ahead of myself a little bit, but features that we could write ourselves were extremely explainable. We could explain it in terms of the function itself. We had the code. This is how we computed these features. Those features are often connected to real-world topics we could understand. So something as simple as how long a sentence is a super basic feature, but it might have some relevance to how complicated an utterance is, and maybe somebody whose cognition is failing has shorter sentences. Somebody who is very cognitively robust, like yourself, might have long sentences. So something as simple as how many words exist in this sentence could be an important feature to make that kind of ascertainment of someone's cognitive function. But if you're just using a neural network that is doing all kinds of things with the raw input, and kind of like we saw earlier with latent variables, like the information is going to be spread out over a lot of different other variables that don't have much meaning on their own, it's hard to explain what a feature is. A feature is no longer necessarily explainable. I'm getting far ahead of myself, but this is something I wanted to mention, because sometimes features are more or less what we're going to talk about today in this module, and sometimes they're just vectors of latent variables pre-computed by neural networks. So there's a function called mermaid here. Yeah, there it is, which draws these things. And when I saw this a moment ago, everything looked fine, but there's a bug here. Regardless, it's not too important. The overall concept we have to deal with is this. We have raw data, and this raw data can be database fields, logs, images, or text, whatever the raw data is. We might also have some leakage. We might have some future labels or outcomes or other information that's available. And this is a bad thing because sometimes this information can leak into our feature engineering. This is the subject of today's module, is this big box over here. This is supposed to be, kind of cleaning, some transformation, some encoding, some aggregation, and some pre-computed features, like I mentioned a moment ago. But ideally, all of that is performed only from the raw data. But there might be some information available to us that ought not be, and that might inform the features we're computing. And if we're doing that, that's a leakage, like we're cheating in some way. That will give us a feature matrix that, when we provide it to a model to do learning and eventually predictions, it'll have seen the cheat sheet and therefore be a problem. So that's a big topic of today, is this unfortunate leakage that can occur. So feature engineering can be considered like writing code. We can see it as, well, we start with some raw columns like text, timestamp, user ID. We want to write small testable functions that map raw data to useful numbers, like I mentioned a moment ago. And then we're going to wire these functions into a pipeline so that they run every time and consistently. So we have some data frame of raw information. We pass that data frame to a function, say called make feature. There's some understandable transform over here, and we return some value that is sort of like the output of this function make feature, and then we'll just store this in a new column, calling it make feature in our data frame. So adding a new column of inputs for our model. This is a tiny example. Imagine we have a review text column with lots of text in it, like lots of words written out in a string. And we want to predict whether this review is positive or negative, because maybe knowing whether the review is positive or negative will be helpful for us downstream for some future classification. Like maybe we have to decide whether or not to put this movie in an airplane, like if we're working for the airline. Anyway, this handcrafted feature is this. Super simple. We have this one function, word polarity. It takes a single word. We have a list of positive words like good, happy, wonderful. This is super, I want to say dumb. That's pretty dumb. It wasn't dumb 10 years ago. So a word is said to be positive. If it's positive, return 1. If it's in a set of negative words like angry, sad, fall, something like that, it's negative. And if it's neither positive nor negative, it's neutral and returns 0. So for any given word, it has this polarity. And then we have this function, average polarity. So given a text of many words, we tokenize it, which means splitting up this long string into a list of separate words. Every word we're going to lowercase. This is a standard thing we do in natural language processing just for standardization. And then we have this list words. For every single word W in that list words, compute the word polarity on the individual word. So call this function from lines 1 to 8 and store that value 1, -1, or 0 in this list scores. So we'll have this list of scores of the same length as words, and then just return its average. So take the average of it, return its floating point value. Only do it if it exists. If the scores doesn't exist for whatever reason, just return 0. This is like just a bit of software engineering. And then what's happening here is we have a single column in our data frame called review text. For each one of them, apply the average polarity function, and then just store that in a new column, average polarity. And we're done. This is classic feature engineering. We wrote some code that turns raw text into a numeric signal. Like most machine learning models, certainly support vector machines from the previous lecture, logistic regression. They're not going to be able to take text yet. We'll shortly see how we can take raw text as input, but we've converted the raw text into just a single number, the average polarity, and the average polarity of the string, how positive or how negative this overall review is, will be a feature that we're going to use. And we can combine that feature with other features, maybe the length of the review, maybe how active this user who posted it is. Maybe we want to de-emphasize a user who doesn't come on too often, or maybe we want to emphasize them because they hated it so much or loved it so much. So we have a lot of other features in a big vector, call it x, maybe call it phi, and provide that to a model. So here's custom transforms in a pipeline. This is just, I mentioned it mostly for the point of view of good machine learning operations, good software engineering. We have, this is not going to run, this is just a sketch. So we have a numeric columns, we have a text column. We are just adding handcrafted features. This is basically doing what I mentioned a moment ago. We have a function transformer. This is adding all our handcrafted features to this feature step. And then this is where we do preprocessing. We do standard scaling on our numeric variables, the numeric columns. And we've also obtained this average polarity now from this transformation. For all of our text features, we do the count vectorizer, and that is part of our transformation. Anything else, just drop it. And then we have our pipeline. Again, we should be thinking in pipelines when you're developing machine learning operations for consistency. Our steps are to compute the handcrafted features, perform any pre-processing, so do the scaling and vectorization, and then do the logistic regression or the classification. And we provide whatever hyperparameters we need for our classifier. In this case, we're doing logistic regression with at most 1,000 iterations. So all of our little feature functions live within one object, which we only have to call once. And cross-validation and grid search can use the same pipeline. So we haven't really done too much of this yet, but a single pipeline will run on one big set of data, which could be our training set, and it kind of isolates the test set in a way that's clean in code and less risky than having some sub-trains and X sub-tests running around. So why do pipelines matter for feature engineering? Well, this prevents leakage, so transformations can fit within single cross-validation folds. So I'm only going to apply a pipeline on a set of data, so any scaling, any transformations will only apply within that data. Again, we talked about scaling on all of the data, including test data. That's not going to happen because we're running it in pipelines. We saw that in previous modules. Again, the example of just looking at words in a single string on a particular data point, that is not at risk of taking other data points from the test set and using information from the test set in our transformed pre-computed features. But it could be the case that when we're running functions, we could run functions on arbitrary data points. Some of those might be in the test set, and then therefore our computed features will have some influence, whatever that is. At this point we don't know, but whatever that influence is on our features on the train set, we don't want that to happen. So putting our feature transformations in pipelines avoids all kinds of problems of that type too. Keeps the code honest. It tells us, we're producing or computing new columns from these feature transformations. We know we're getting them from our feature transformations. Any scaling or pre-processing, like we're not doing that manually in some other cell, of a Jupyter notebook. It's all happening locally in the pipeline, and it's clean too. It looks nice, and it makes it reproducible. So this isn't the same thing as running everything within a ML flow, which is something I think I mentioned, which I might come back to later, like this reproducible libraries for ML ops. But it helps, if everything's in a pipeline, it helps keep things reproducible. So when you're reporting something, other people can get the same results as you, to make sure you're not telling tales out of school, so to speak. We're often going to start with, so often before you get to pipelines, you might mess around with feature code and play around with it and just make sure and debug and be a bit more loose with regards to the software engineering practices. I think it's not perfect, but it's totally fine, and it's a bit faster to do quick iterative improvements. But then once you're comfortable that your little functions that we're computing are correct, then we'll graduate by putting things into a pipeline once we're happy with our little codelets, I guess you can call them. So here's the types of features. This is a kind of a tabular focus. This is back to kind of how we've been talking about machine learning so far. Income, temperature, counts, these are all kind of standard inputs. We've been calling them X so far. We can do transformations to them, so we can standardize them. This is the standard Z-score. We can do min-max scaling, so we could, if we have ranges in all kinds of areas, we could find the mins and maxes on the training set, and then recompute what X should be within that range. That's another form of feature engineering. It's not computing something like as interesting as it's interesting from my point of view as polarity on text, but it's still feature transformation. We can do log transformations. If you have positive, very skewed data, dampening things with a log might be something you might want to consider. That also counts. Categorical data, so countries, product types. I think we've talked about one-hot encoding already. So we're changing a label into a vector of zeros, but with a 1 in an index representing the label. That's a way to transform something which is not easily fittable into a input of a machine learning model. Converting these labels into one-hot encodings is always preferred, from anywhere from a logistic regression all the way up to a transformer-based neural network. You might do some ordinal encoding if the order is meaningful. So if you do binning, if you have raw age as a numeric count, and you might convert it to an ordinal. So 0 to 18, 19 to 35, 36 to whatever, might be converted to 0 and a 1 and a 2. As long as the order is meaningful and the distances are meaningful, this is something you can do. Binary flags can be features, and counts and rates and other kind of proportions can also be features. This is sort of somewhere between a tabular focused, re-representation of our data, like we're talking about right now, and the kind of domain expertise sort of feature engineering. Let's see, move myself. There you go. That I was talking about before. So interactions between ratios. So maybe that one feature is not really informative on its own. A second feature might not really be informative on its own, but the relationship between these two features together is very relevant to your classification task, your machine learning task. Maybe you also know that linear models are not going to sufficiently separate classes using these two variables, but if we can combine them together, this creates sort of a nonlinearity. Simply multiplying two variables together is a nonlinearity. Similarly, taking the fraction or the ratio of these two is a nonlinearity. Maybe the square of one divided by the cube of the other. I mean, this is getting a bit silly, but simple ratios between variables is helpful and is another way to transform your data in a way that you get a feature which is potentially useful for your classification task. A bit of conceptual scaffolding. This is brief, so it doesn't deserve its own section really, but it's just about distances and scale. So consider two observations with two features. We have our heights in meters here, and we have our income in dollars here. So these are just arbitrary for the sake of illustration, but you can see one variable has a divergence of 1.5 to 2, or a distance of 1.5 to 2, a range of 1.5 to 2. The other one goes between 1,000 and 1,000,000, right? So these are obviously on very different orders of magnitude. If you were to take the Euclidean distance between these, if you were to have a kernel function that's just the squared distance between these, you'd have the x again is the height. X is a variable of these two features, height and income. So it would be the distance in height between these 2 points squared plus the difference in income between these 2 points squared, and that sum is square rooted. This is the Euclidean distance we've seen many times before. This could be part of a kernel function that we would apply to something like support vector machines. If you don't scale, then income is going to dominate this distance, obviously. Like the distance between 1,000,000 and 1,000 is way bigger than between 2 and 1.5. So this distance is going to look arbitrarily large if you don't scale yet. After scaling, both of height and income are going to be represented not in meters and dollars anymore, but in some non-unit. But the mean of this non-unit will be 0, and the variance of this non-unit will be 1. And then therefore height and income will contribute more comparably to the distance, which is potentially part of our kernel function. We've talked about this quite a bit already, but it's worth mentioning again and again. Here's our anti-example. So historical features that secretly sees the future. This is an example of where that leakage is happening in our overall conceptual pipeline from that graph I showed a moment ago. Imagine you're predicting a 30-day hospital readmission at the time of discharge. So as a patient, they're in the hospital, and then you're thinking, should I keep them in the hospital for another day, or should I let them leave the hospital because they're healthy enough to go home? If they're going to be back here again in 30 days, maybe it's worthwhile keeping them in for an extra day and helping them out a little bit more, stabilizing them more, or getting more information to see, okay, fine, I'm now more confident that they won't be back here in 30 days and we can send them home. So we want to make this prediction at the time of discharge. So when we make this prediction is important. Imagine we want to add this patient level feature, like the patient readmit rate after 30 days. So imagine this patient is coming back to the hospital over and over again, and we want to measure the fraction of this patient's stays that are followed by a 30-day readmission. This is similar to the ratio feature that I was talking about engineering on a recent slide. So we can compute that by something like this. We have the patient readmission rate in our data frame. We just group by the patient ID. We can see these are instances of them being readmitted within 30 days. Taking the mean of this will give us basically the rate. We have lots of instances of them being admitted. Those are all the ones. We have those not being readmitted. Those are the zeros. The average will just give us the proportion of times that they were readmitted. And then this proportion, this rate, let's rename it as the patient readmit rate 30 days, which is this new feature I want to add to my data frame, my data that I'm storing in pandas. Actually, and then I'm going to merge this new patient readmit rate. I'm going to merge it by using the patient ID as a sort of key, merging it left. This is just a bit of pandas. And then I get my new data frame, which is my old data with my new variable, patient readmit rate after 30 days. This looks fine, right? All I'm doing is just computing these simple proportions. How often is this patient coming back within 30 days? This gives me a rough estimate of how likely they are to come back now. This is like a prior probability in some sense. Now, the problem is this group by that I've just done uses all of the data in the data set. It uses all of the rows in the data set. Maybe I've been careful and you have focused on just the training data. So I've mentioned this many times, you know this by now. I've done the clean thing by not letting validation data or certainly test data leak into my training. So this data frame is only training data, but this data frame can also, I'm speaking slowly so I can go ahead and do this. This data frame can just be training data, but the training data can be can include. Let's see. Pardon me. There we go. This training data can include information like I haven't sort of split the data according to time, right? So like the patient, I have lots of training data for this patient. I care about making a prediction at a particular point in time to understand, like, given this particular admission of this patient to this hospital, I want to make a prediction about whether they'll be readmitted or not, okay? Now technically, if I'm envisioning this as a real deployed model, I'm only ever going to have data recorded up until that point. Okay, like I'm not doing a general model of admissions. Like I want to estimate a real risk estimator for real patients at a hospital and making decisions about whether they should stay or leave, right? Now, if this is the first time the patient has been admitted, I have no historical data for them at all. So for that particular moment, that particular instant where I decide to send them home, in the training data set, I I don't have any other data for this patient. So this group by would give me nothing. But in this instance, where I'm doing training of a model, I have all of the visits of this patient, all the stays of this patient to the hospital. Therefore, I have all of the future stays for that patient after their first instance. But when I'm making a prediction about their first visit to the hospital, and I'm computing things in this way, I've computed the proportion of all of their readmissions to the hospital in the future as measured in reality. And I just wouldn't have had that information at that particular visit. So again, I'm kind of spending a bit of time on here to try to separate this problem from the problem of leaking test or validation data into training. But hopefully you understand this now, right? Like, I'm going to make a prediction for this instance. And I want it to be based on all the information I have available to me at that moment in time. But in reality, I would not have any of the future visits of this patient because the patient hasn't come to the hospital again. So it doesn't make sense to take a proportion of all of that patient's readmissions to the hospital over all of their admissions in the training set, because that just wouldn't be available to me. Again, hope that's clear. So this group by uses all the data, including future stays. Therefore, this patient readmit rate, 30 days, will, quote, know how often this patient is readmitted later in the timeline, and that's not great. So this will end up giving us performance that's too optimistic. Maybe this patient has a particularly virulent or serious disease, so they're going to be readmitted a lot more. Maybe they're not going to be readmitted very often. Maybe they're less prone to disease and they won't be readmitted very often. Either case, knowing that beforehand will give you better results on training at the very least. So it'll be optimistic in terms of training. A deployed model, so when you actually deploy this, will simply not have information about the future, and it'll perform much worse. So especially if you have a new patient the model's never seen before, it won't have access to this kind of statistic. So even if we used a pipeline, even if we put everything into a pipeline and made sure that we're only computing these handcrafted statistics on the pipeline data, like we talked about a moment ago, we could still end up with this problem where we're being too optimistic and features are reflecting information that's not going to be available to us. This is somewhat subtle, but you'll be surprised at how often people ignore this kind of problem in machine learning. So a little bit of under the microscope. Back to a linear model with L2 regularization. This is our good old-fashioned model. We're trying to minimize the loss, and we're trying to minimize this L2 grid regression from the previous module. Now imagine we have rescaling a feature. So we have the original feature is x sub j. We scale it by some factor s, and this gives us a new feature x prime sub j. So to keep the same predictor, wx, so we had this previous predictor, but now we scaled things. We would need to modify everything. So we would need to, to keep the predictor w prime sub j times x prime sub j being the same as w sub j times x sub j. We would need to also scale our weights by the same factor s. So you can work this out yourself, but hopefully this should be obvious to you. But the regularization term also needs to change. So we have our regularization term here, lambda, and this L2, this 2 norm. We have a lambda, and then we have our sum, a sum of the squares. Each one of these are going to have to be divided by s as well. So the point of mentioning this is when we rescale features using something like a standard scaler, this will actually change how strongly each feature is going to be regularized also. So it's not just that we're scaling things for the point of view of the loss. Like I talked about, the influence of height and income because of the differences in the units are going to have differential impacts on training. This is also true of having an effect on regularization itself. Rescaling features will have an effect on how strongly each feature will be regularized. So in practice, you should scale numeric features before you do regularized models. This is normally handled for you automatically in pipelines like we saw before. We do a standard scaling at one step, and then we do our modeling. And in the modeling is where we have our objective function, which is where we specify that we're doing L1 or L2 regularization. But we do that, on scaled features on the training set. So regularization strength will be comparable across features. Like, again, the same intuition applies. If we don't do this, we don't want, a regularization to overemphasize or underemphasize certain features based on their original units. They should be based on the standardized scaled units. So I wanted to say about that. This should be kind of obvious anyway. Here are our good old-fashioned examples. Here's just we're going to need all of these libraries in our code, so we load them in this big Jupyter notebook. Our goal is to see how feature scaling interacts with logistic regression. So we're going to do good old-fashioned logistic regression again. We're going to do some feature scaling, and we're going to use an actual breast cancer data set from scikit-learn. So we can get that over here from sklearn datasets, which has lots of nice smallish datasets for you to play around with. We import the load breast cancer dataset. It's fairly standard. You can read more about it at the link. We have our data and our targets, and we put those into our data frame. And this is just what it looks like. Nothing really to write home about yet. We just have lots of features. And we have a mean radius, mean texture, mean perimeter, mean area. All these features are provided to us in our data set. Each row is a tumor. The features, the columns are cell measurements. And the target over here is whether it's malignant or benign. I think benign is 0 and malignant, which is cancerous, is 1. And we're going to do classification based on all of this information. So example 1 is just doing unscaled versus scaled logistic regression. We have a plain logistic regression where we're just doing straight ahead logistic regression, and then a pipeline in which we're using a scalar first, and then we're doing logistic regression. We have our cross-validation score here. We're doing cross-validation with k equals 5. We have our plain scores across each of the folds. We have our scaled scores across each of the folds. And then we run everything. We have our data frame, a new data frame called results, which is our setting. We have our accuracy scores, the average accuracy scores across our 5 folds, and we have our standard deviations across the 5 folds as well. And then we're just going to look at the results. This is what we get. Our mean accuracy across the 5 folds in the unscaled version is 95.3-ish percent. With the standard scalar, we get up to 98-ish percent. And we also see the standard deviation on average is a lot smaller by an order of magnitude. It's shrunk by a factor of 3-ish from about 0.019 to 0.0065-ish. So that's good, like we're getting, through all the folds, on average, we're getting better accuracy on average, and we're getting more consistent performance on average. Our standard deviation, like the standard deviation of all our performances, is getting tighter. And like we talked about before in the, the data sets, cross-validation modules, we prefer modules to be consistent. So they perform very well, and so the standard deviation is tight. Same model, everything else was the same. We passed the same hyperparameters, the max iterations to both of these. The only difference was feature scaling, and scaling improves stability, and often, in this case in particular, it improves performance for these linear models. We can actually do a little bit of explainability here. This isn't really explainable AI yet, but it's sort of like putting our feet into the shallow end of the pool in terms of explainability. We can inspect the magnitude of the learned coefficients after scaling. So we can take the our pipelines, the scaled version. We have all of our named steps. We can take the log reg from each of these, and then if we sort them, or if we get the coefficient vector, then we can sort them by their magnitude. And then this will give us a relatively simple measure, a super simple measure of importance. So we've scaled all the inputs. We've done any kind of regularization. If we have regularization, will also be scaled. And then what we end up with using this regularization is the magnitude of the coefficients we're getting is a proxy for how important they are. I think we've talked about that a little bit in a previous module anyway. So here's all we're doing. We have our train test split. We fit a model. We get our coefficients. And where we store, here we're sorting them. So yeah, we're just getting their absolute values here. All of our coefficients. I mean, like the difference between a highly negative and a highly positive coefficient is not relevant to us at the moment. So we take the absolute value of these, and then we sort the absolute values of these descending. And then let's look at the top 10 of them. So what are the 10 most important features for predicting whether this tumor is malignant or benign, whether it's cancerous or not. And we get this ranking. So the most important feature with an absolute coefficient of 1.3-ish is worst texture. The second most important coefficient with a feature with coefficient 1.08 is radius error, and so on. I don't think I'm going to mention this later. I might, but I point out that these are looking at these features independently, like separately, right? So worst texture by itself had the highest value of the coefficient when we trained our model. So our model kind of tells us that this is the most important single feature. But sometimes features can interact with each other in interesting nonlinear ways, and we're not really getting that out of this analysis. If you were to guess that worst texture and area error, or maybe say radius error and area error, that's maybe a bad example, worst concavity and worst area could interact in nonlinear ways, then you might take the ratio of them together, you might multiply them together, you might combine them in some other nonlinear way through using a feature map like we saw in a recent module. This would be a new feature which you'd provide as an input to your modeling, and then maybe that new combined feature with these two original features together would give you a higher absolute coefficient than any of these others we've provided so far, right? I mean, this is getting to be a bit of an aside, but this is a way to take all of your inputs and see which ones are the most important to getting a good classification, and you can just rank them like this and then just take them. Maybe you take this list to, in this case, a doctor, like an oncologist, some expert in the area, and say, this is what the model thinks is important in terms of classification between benign and malignant. And then the doctor would say, oh yeah, this makes sense. Like I know that worst texture and radius error are important for me to making decisions. And this is a form of explainability, which is a whole topic in machine learning, which we'll hopefully have time to mention later in this course. And that's all I wanted to say really here. This is the same thing, just visually, nothing much is happening. You can visually see, like, in a way that might not be obvious here, looking at these numbers, like the magnitude of differences between the most important feature here, worst texture, and the 10th most important feature, worst smoothness. So usually when we do this kind of reporting, we might do a kind of a graphical representation. That's all it really is. So larger absolute coefficients mean stronger influence on the log odds, keeping everything else fixed. If you try this again without scaling, again, I invite you to try to do this exact example without scaling and see what happens to your ranking and to their magnitudes. The key observations here, simple models like logistic regression can rely heavily on feature scaling. Coefficient-based interpretation will only make sense if the features are on comparable scales. Like we wouldn't want to look at these features and say, well, one feature is much more important than the other if any differences are, really a function of the magnitude of the units. So that's why we're doing scaling. Regularization is also important. If we were regularizing these features based on regularization that was not also scaled, like we talked about using the microscope slide, then that would be also kind of a problem, like we would not be doing our job properly. So question to ask, are my features, are they on wildly different ranges? Am I computing my models fairly? Are they using the same splits? Are they using the same preprocessing? Ideally that's the case. And do your interpretations depend on units? I mean, not mentioned here also is what I was just talking about also, like if you're doing a feature sorting in this way, you have to remember that these are looking at these features one by one independently, and it's ignoring any kind of interaction between these these features, which might be extremely important. That was example 1. Let's look at example 2. This is a target leakage example. So here we want to see a too good to be true performance, and see this as an example of the kind of leakage I was talking about before. We're going to make a simple synthetic classification data set, and then we're going to train a logistic regression model on the original features only, plus a feature that is leaky, that's going to encode the label in some way. This is what we've been talking about quite a bit in this module and in previous modules relatedly. So we're using the make classification function, we're going to have 5 features. 3 of them are informative. None of them are redundant. There are 2 clusters per class. There's 2,000 samples. We have our random state. And then we do a logistic regression. We're not doing any scaling now or anything like that. And we get our base score. Okay, so our base score is already pretty good. We get an average of 91.3% accuracy, and the standard deviation seems to be relatively small. So this is a good, reasonable baseline. Sometimes you see people using baselines that are just way too easy, and that's like, you should never make things easy for yourself. So example 2, we're going to add this leaky feature here. So here we have X leaky is a stack. We have our inputs X, and we have our labels Y, or outputs Y. So we're going to append the true label as an extra feature. So this is not allowed in reality, so I'm making sure this is a what not to do example. We stack them together, and then we're going to compute a cross-validation score on everything. This is the most obvious case of leakage. This is much more obvious than the somewhat subtle things of like the patient whose risk of readmission computes future information that we don't technically have at that moment for that data point. And it's also more obvious than other forms of leakage, where I'm leaking information about the label into the input. Like here, I'm literally passing the input. I'm actually literally passing the target Y into the input X. So I have my leaky X with the Y's included. I'm going to compute my cross-validation score. I have my base model. I have my now leaky inputs. My Y's do cross-fold validation, and then compute everything. Originally, I had a cross-validation score. The accuracy on average was 91%. My standard deviation was nice and small. With this leaky label, all of a sudden I have 100% accuracy. I mean, obviously I do, because I've stored everything in my inputs, and I have a standard deviation of 0 because I'm perfectly performant. This is like an extreme example, but we have even when we start with a very strong baseline, we can get much higher accuracy if we've leaked information into our inputs, and that is a massive no-no. Some might even consider it to be cheating. If you were to do this in practice, your job would be at risk. Here's again just a visualization, this time in terms of the mean accuracy and cross-validation. No information here. So that's very pathological, but here's more realistic leakage patterns out for which to watch. In real data, leakage is more subtle. It might be that you're aggregating features and you're computing this with some kind of knowledge of the outcome. So this actually, I'm happy to tell you this anecdote. We never published this, but at one point during an experiment, this happened to us. We were, again, trying to use someone's speech and language to determine whether or not they have dementia, this cognitive disease. And we had all these measures, all these computed features of how many words people use, how complicated their grammar is, some information about polarity, are the words positive or negative. We had initially dozens of these features and eventually thousands of them. At some point, I can't remember when, we also had something called a mini mental state exam, which was, this means that a clinician had talked to the patient and had determined that their level of cognition was somewhere between 30, which means perfectly healthy cognition, down to something like 12, which meant dementia. And we passed, because we had that information, we passed that as input, X, to a classifier We got extremely good classification performance. And we were like, well, like the labels, the actual diagnosis, dementia or not dementia, was held out. We're not using that label anywhere in any of these computed features, so we're not leaking any data. But, so technically, this is a little bit more so. I mean, it's obvious, it was obvious to us pretty quickly also, to be fair. But, even though we're not leaking like any of the labels Y into our computing process of X, we kind of are, because the doctor who produced that mini mental state exam produced a score. That score is used to diagnose somebody with the disease. The correlation between that feature and the disease was basically 100%. So including that feature as input, because it correlated 100% with the outputs, gave us really high performance. Actually, I don't think I mentioned this here, but that's a pretty easy way to check whether or not you might be leaking information into a classifier that you might not have, is to do a simple correlation between each of your features and the output. And if any of the features has 100% correlation with the output, then that should raise a flag, and that should make you investigate what's going on. It doesn't mean necessarily that, that's bad. So sometimes you might have a feature that does have a very strong degree of correlation with the outputs, and maybe that's perfectly reasonable, but by going into the data and just checking, that would reveal something like this error that we encountered. Why is it an error to have mini mental state exam as input? Well, we're trying to use this model to replace humans to do diagnosis. And if we have a human already doing a diagnosis, then that kind of breaks our mental model of what the classifier is for. So go ahead and do correlations for all of your features and the label. If any of them are 100% or close to 100%, then, or negative 100%, like 1 or minus 1, then look into those correlations and see if there's anything fishy going on. So that's basically what we're talking about here. Some final thoughts, some pipelines to reduce mistakes. The bad style is to have everything just sort of stretched out like in a linear form like this. You're doing your train test split, you're doing a scalar, you're running a scalar somewhere, you're running a scalar on train and test like this. Even if it might be correct, even if you're fitting the scalar only on the training data and applying it only to the test data, this is actually correct, but it's easy to forget that you've written it this way. It's easy to later on add extra steps or copy and paste things wrong. Better to just start with a pipeline as early as possible to put the scalar in the process this way, and then to fit and score separately like this. Bad style above, prefer pipelines below. Again, pipelines exist in scikit-learn. They also exist in Hugging Face for neural network models. So the advice scales. All preprocessing steps should live within the pipeline, and cross-validation in grid search will live outside of the pipeline, but we'll keep everything in sync because it'll always use the same pipeline. So also feature engineering can also introduce ethical issues. Again, these are unique. So you might have a lot of data, and you might have race and gender and disability status, these kind of protected attributes. And you might want to remove them. So because of privacy, you might just take those columns in your data frame and cut them out, and then do that early, and then do some processing later, which is the right thing to do. But you've forgotten that there might be a high degree of correlation between postal code and race. I'm not really necessarily how sure this is, but the story goes that, well, if someone lives in Little Italy, there's a higher probability that they might be Italian, or if they live in or close to Chinatown, there's a higher probability that they might have Chinese origin. I don't think that's necessarily the case, but even small changes in probability to those, the relationship between race and postal code could mean that if you still have postal code in your data set, you might be encoding some information about race, which you thought you've removed. There might be some correlation between disability status and income. I'm not sure if that's true either, but in case that's correct, removing disability status, the information might still persist in other proxies for sensitive attributes. So you need to be careful about that. Again, a mitigation is usually to document everything you can. Documentation can be considered to be boring, but a really good documentation can be a work of art, and it's good to keep. Also, it's important for you to be able to go back and diagnose these kinds of problems. Again, check performance on subgroups, like if you've only done classification on these proxy-sensitive attributes, are you still getting differential performance for the different racial groups, different ability statuses, and so on? And maybe there's some structural biases that still exist that still need to be dealt with. And remember, just because a feature is very predictive doesn't mean it's acceptable to use. Obviously in the case of having a mini mental state exam, if we were to sort all of our features in that experiment, mini mental state exam would have come out with a high absolute coefficient in terms of prediction from a model that uses it, but it predicts it because it's like a shortcut to the answer, right? So it's not acceptable from the point of view of machine learning. And similarly, using someone's income or postal code might not be acceptable from an ethics perspective in a model. So you have to deal with these external to the training. I want to mention this again at the moment. I think I'll keep coming back to this anyways, but machine learning can't just be about writing the code and then getting the numbers. At the very least, you have to frame this within a scientific context. I keep on trying to emphasize how important it is to be reproducible, to check your biases, to check your assumptions, to document everything, to do science as well as possible, to always try to seek for the truth. That should be the baseline for anybody in a university setting, to try to be the best scientist you can. But beyond that, we're going to be leaders and engineers in reality, and we have to think about the bigger picture. So where does this show up in practice? Feature stores come up often a lot in industry, like in research papers using cutting-edge machine learning. We might de-emphasize features, just for the sake of modeling. So we might be convinced that methods are more important than everything else. But in reality, if you work in a bank, in a hospital, in the Halifax ports, you might be more likely to see feature stores, like big databases that have centralized, versioned features that are shared across teams, not just the machine learning data science team, but across marketing and other decision-making teams. So they've been kind of massaged to a large extent. So we're dealing with data in a very processed form that is not as clean as we might like. Oh, I did not notice that this is happening. Let's try to see if I can move myself again. Or not. Okay. Automated feature engineering, so tools that might search over transformations, interactions, aggregations. In deep learning, many architectures perform representation learning. This can be all in one big pipeline, or you can have two separate pipelines where we do our representation learning first, and then that gives us features, like neural network features, these latent space features that we pass into classifiers. To a large extent, this is what massive large language models are doing, or even pre-trained language models that predate large language models. They have a tokenizer. So a tokenizer would take just a string and split it up not only into words, but into subword units. A model has to learn how to do that. And then it takes those representations and those embeddings, which we'll get to later, and then pass those representations into another model. So if you've ever seen BERT before, or any of these pre-trained language models, you'll see that there's actually two models side by side, and the first provides features to the second. We started looking into explainability a tiny bit in terms of feature importance in models. This is related to SHAP values, which is like a super popular method of explainability across disciplines, and it's much more robust than the fancier explainability models that occasionally come up. Counterfactual explanations and reasoning, are a bit beyond what we're talking about now, but they often, at some level, make reference to low-level features. And it helps to debug, right? So if you end up with situations where features become way too performant or relevant, we want to align them with domain understanding. So we're going to be working in big teams. We're going to be working with doctors and doc workers and MBAs and bankers. Wherever we end up working, they're going to have their own understanding of how the world works. So how we explain the ranking of features to them should line up with their expectations. And if anything's surprising to them, if anything's missing, if anything's added, we have to be able to work with those other teams to make real-world decisions, which is a lot of fun. It's a big part of machine learning in my estimation. Here are our quick checks. Please go ahead and do them. Features can be considered to be the language your model uses to understand the world. Good feature engineering is grounded in the data generating process. We want to understand how the world works. We have to be careful about scale, about leakage, about availability. This is in reference to the readmission, for example. We need to, as much as possible, encode things in pipelines. So like sometimes you can have ad hoc scripts. A lot of graduate level and professor level research is kind of sloppy. But as much as possible, as soon as possible, when you're comfortable with your feature engineering, we want to put these into scripts. Into pipelines. And then all these tools will set us up for our future modules. So next we're going to talk about data augmentation in module 24. And then beyond that, we'll actually talk about data reduction and learned representations in later modules. So we're building all these representations in terms of features. We'll augment features soon, and then we'll reduce them a bit later on. This is a lot of fun. This is some of the stuff I love most about machine learning, and it's a pleasure to present it. And as usual, I'll see you next time.